Hey, how is everyone doing? Welcome back to my TikTok channel. In this video, I would like to share with you a quick trick about how to use Houdini to visualize the draw calls in your game environment and help you optimize your game. So here's the trick. Don't draw anything. Okay, now you've been subjugated to my bleak sense of humor. We can talk about how to take this beautiful scene and convert it to something like this, where separate colors indicate separate draw calls. Alternatively, in this version, different colors represent different materials. As I scroll through to show you more examples, I'd like to talk a little bit about the fundamentals of draw calls. As you probably know, draw calls can have major performance impacts. These impacts depend on the hardware the game is running on, but in general, having too many draw calls tend to slow the game down. Draw calls are commands sent from CPU to GPU to render something, and these commands are not very cheap to send. The two parts of the pipeline, CPU and GPU, have very different architectures. If draw calls are too granular, GPU tend to be able to execute them faster than CPU can send them, resulting in GPU having too much downtime doing nothing, therefore not running at full efficiency. Therefore, a frame takes longer to render. What constitutes draw calls in a frame is complicated. Shadows, lights, effects, skeletal meshes, motion blurs are all part of the equation, but it's often useful to start with fundamentals, in this case, your environment, because what they tend to be are the base draw calls that will be multiplied against. For instance, when you have two chairs using two different materials, the base draw call is 2, but for every dynamic light from which the chairs are casting shadow, that is 2 additional draw calls. For the cascades of a directional light, which usually has 2 or 3 shadow cascades, that is 2 additional draw calls per cascade. Reducing draw calls do not necessarily mean reducing visual quality. There is often a realm where you can improve performance and maintain quality by avoiding excessive draw call separations and by cutting down draw calls that don't add much to the visuals. That is why I created this visualization workflow in my last project in production to help my environment artists discover places where we can reduce draw calls. A draw call is calculated per mesh per material. So one thing I need to point out is that this visualization is overly aggressive in one particular situation. Some game engines do not have the ability to batch draw calls dynamically. That is, if the objects are using the same material and referencing the same mesh. It's basically mesh instancing, automatically set up by the engine and not by the artists. But since it's not user-defined, you have less control over it, so it doesn't hurt to be overly aggressive in generating a warning with this visualization. You can then use profiling tools to verify if those identified meshes have indeed been automatically batched or not. In this image, the pipes, which use Unreal spline mesh components, do not batch. Each color section of the pipe is its own draw call. Now let's jump into the engine and let me show you the whole process of how to get this done. Now the first question is, how long does this whole process take? It's about 10 to 15 minutes. It's relatively fast, that's why I was able to do it daily, as the environment artist update the environment and I can generate a new visualization every morning if I needed to. So you first need to understand the asset structure in your scene. Like for this demo scene, for instance, I don't need the cameras, I don't need the lights, so I can just search them and delete them. The purpose here is to export the meshes I needed to visualize. So if I delete them, it doesn't matter. I'm not going to save the map. Other things you might consider deleting are decals too. Now this map doesn't have decals. So let's say I'm exporting all of these. So what you need to do is go to File, Export Selected, and pick a location that you want to save it to. And this is the export setting I'm using. And just click Export. Now that you have exported your scene geometry as a FBX file, you can then open Houdini and go to File, Import, FBX and click on this button to navigate to the location where you saved your FBX file. Then click on import. That will bring in a subnetwork that looks like this. I'm just skipping that importing process to save some time here. And the first thing you can do is change the uniform scale to 0.01 because in Unreal the unit is centimeters, whereas in Houdini the unit is meters. So inside this is basically all the objects that you brought in from the game. Now this whole file here, I will provide it to you in a link under the video, so you can just see how I set it up. It's really simple. Here we have geometry. Inside we start with the object merge node, where you can navigate to the FBX and just add a / asterisk that will bring in everything underneath it. So first thing I want to show you is there's some important properties that were brought in here, which is object name and shop material path. So this material path describes what material is applied to each individual object, and the object name here indicates the name of the object. Now one thing we need to do first is that the object name is quite long because it has a lot of repetitive path, and same goes for the shop material. So what we want to do here is to trim them down by taking basically the last token of the whole string in the material path. And for the object name, we will remove all the repetitive parts, like from here obj and the FBX, or that part. So that's what this node is doing. So we identify the common path in the object name and slice it, so that now begins our draw cross string. Then the material token is divided by the / and we take the last token and we combine the material with the draw call string, and that gives us the final draw call string. As we said before, draw call is based on per mesh, per material. So each unique combination of a material name and mesh name give us the final draw call. So based on the draw call string, as you see here, material, mesh name, we can use random color to basically show this is all the materials that's being used here, and these are the draw calls. Then we just promote the color from primitive to vertex or point. I have a note here, so most of the time it's fine to promote it to vertex. Sometimes Unreal, during import, they will split the vertex in a different way, so create some kind of mismatch. So if you see that happening, you can change it to cd to point, then that will work fine. I've tested it. Then we'll just remove all the unnecessary attributes, assign a principal shader, which is just, you can go to the material palette and just drag that over here. It doesn't need to change anything, just apply that, so everything has the same shader. Then we'll convert back to the Unreal unit by multiplying 100. Then we'll export. So just need to set display on this. Here's a toggle to decide if you want to export the draw call version or the material version. Then we go to File, Export, FBX, choose the path, and set this to game worlds, and click export, and that will do it. Now we can go back to the game engine and grab the FBX file we exported from Houdini and bring it in. So this is my import setting. Most things are unchecked, and we just need to make sure that the vertex color import option is set to replace. And we don't need to create a material in this case, and just click on import. Now that's being imported, we can open it up, and I'm going to choose a material I created called M vertex color. Now we have it. this gives us the visualization of draw calls. So this is what's inside that. It's a very simple material. You just have a two-sided chat. And you see Z fighting here. That just means that in the original mesh there are planes that actually are on top of each other. So that's not a mistake. Then you can fly around pretty easily to inspect your scene and see opportunities for optimization. Now I want to point out a special case, which can in fact happen quite often, is when your artists have already set up some user-defined instances in your scene. So we want to tell the process to treat the instance mesh as one draw course instead of separate draw course. So here we have 30 chairs and 6 different materials, and we're gonna do the instance ourselves. So we'll have them selected and right-click on them and say merge actors. We're gonna choose the third option because the first two is more destructive. They will merge everything into one mesh. That's not what we prefer. And merge actors. Now what happened is all the chairs look the same. It's just the original ones are set to hidden in the editor and hidden in game. A new actor has been created, which contains the 6 instance static mesh component, and each component corresponds to one of the 6 different materials, and under each component there are 5 chairs. So these are the instance meshes, and the original meshes are there for you to undo the process if you want to. So we can export them. Export selected. Now we are back in Houdini in a new file that is empty currently, and we'll just go to File, Import, FBX. I have already tapped in the address here, and just click on Import. Now, as I said before, set the scale to Houdini scale. That's the chairs. So what will happen if I just repeat the previous process is that I grab the chairs and I visualize by draw call. Here the information is mistaken because there should actually only be 6 different draw calls, as each row of these chairs are instanced. So there's only one draw call here, but here we're visualizing 30 different draw calls. So in order to fix that and provide more accurate information, we need to do a little bit of hack here inside the subnetwork. The reason there are 30 different draw calls is when OptiMerge, it was trying to merge in different objects, it was looking at each individual nodes here, the leaf nodes, as they are all unique. So what we need to do is to basically grab the content inside each leaf node and merge them back inside here, inside the instance static mesh component, because that's what counts as a draw call. In order to do that, it could be a very lengthy process if you have a lot of instance mesh in your scene. So I wrote HDA here that's basically based on some Python code, and I'm just going to drag the top of the hierarchy to here and click on that. Now all the leaf nodes are merged in to the branch nodes. That's what we wanted. So this HDA will be provided you as well, and there are 2 tips on what each one of these buttons does. So the manual option basically lets you specify this. You can drag this node into the manual option, and that will merge the immediate children after that. And the top of the hierarchy just merges the entire tree, just to save you some time. Then we go back to game world. Now this is correct. That is that's basically the end of this demo. So hopefully it will be helpful to you. And like I said, I will provide the demo file and the HDA, so you can use them however you want. Thank you.